The Higgs boson is the particle that gives things mass. But how does it give mass? How do we create them? And how was it discovered? How does the Higgs boson give things mass? Low mass objects are easy to speed up, but high mass objects are hard to speed up. Why? Well, imagine a massless particle like a photon flying through space. With no mass, it's very easy to speed up. In fact, it's always travelling at the highest possible speed, the speed of light. But if we trap the photon in a box, it suddenly becomes harder to speed up. Why? Well, the photon bounces off both walls at the same speed, exerting equal forces on both walls, which cancel out. But now, if we try pushing the box to the left, the photon bounces off the right wall faster than the left wall, exerting a bigger overall force to the right. The photon is pushing back. In other words, interacting with the box has given the particle mass. But particles aren't really trapped in boxes, so what really gives them mass? Well, in 1964, Peter Higgs and 4 others proposed a theory. Rather than a box, particles really interacted with an invisible energy field that permeated the entire universe. They called it the Higgs field. Particles which didn't interact with the Higgs field were massless, particles which interacted weakly had a small mass, and ones which had strong interactions were heavy. But how could he prove the existence of the Higgs field? Well, Peter Higgs knew that the fabric of space was made of 16 energy fields, 12 matter fields, and 4 force fields, which let matter communicate. He knew that they existed because each field had its own particle in what's known as the standard model of physics. For example, the electromagnetic field has photons, the electron field has electrons, so if the Higgs field existed, it should have its own particle, the Higgs boson. So, discovering the Higgs boson would prove that the Higgs field existed. But Higgs bosons don't exist naturally, so how do we make one? Well, in the same way that ripples in water create droplets, sufficiently big ripples in energy fields create particles. This is done using supercolliders, powerful machines that accelerate particles to near light speed and smash them together to create a sea of new particles. And because energy and mass are equivalent, heavier particles, like the Higgs boson, need more energy to make. But Peter Higgs didn't know the mass of the Higgs boson, so finding it would take some serious detective work. So began the 50-year search for the Higgs boson. Attempt 1 at creating a Higgs boson was the LEP collider in 1990. It was a 27-kilometre underground tube which accelerated electrons and positrons to near light speed and smashed them together to create a sea of new particles. Each collision had an energy of about 209 gigaelectronvolts, about 1/5 the energy of a flying mosquito. Now this seems small, but at such tiny scales, the energy density of each collision is over 3 trillion times more than the Sun. The LEP could search for masses up to about 114 gigaelectronvolts per c², but no Higgs boson was found. So if it did exist, it had to be heavier, and a more powerful collider was needed. Attempt 2 was the Tevatron in 1995. Rather than colliding electrons, the Tevatron used much heavier protons and antiprotons to give each collision more energy. The collision energy was now 10 times larger than the LEP, at about 2 teraelectronvolts, roughly twice the energy of a flying mosquito. Small signs of a new particle with a mass between 115 and 135 gigaelectronvolts per c² was seen, but only with a 2.9 sigma certainty, almost enough to be classed as evidence, but not enough to reach 5 sigma and claim a discovery. A collider with a much higher collision rate, or luminosity, was needed so that more Higgs bosons could be made. This finally takes us to the Large Hadron Collider in 2008, the most complex scientific instrument ever built. Using the same tunnel as the LEP, 2 opposing proton beams are accelerated to near light speed and are collided inside a detector at an energy of 7 teraelectronvolts, about 7 flying mosquitoes. To ensure the results were true, 2 separate detectors, the ATLAS and the CMS, searched for the Higgs boson independently. But proving that you've made a Higgs boson is harder than you think. 1/trillionth of a billionth of a second after being created, a Higgs boson suddenly decays into other particles, like a pair of gamma photons, so we can't actually see a Higgs boson directly. Instead, a detector measures the energy of the photons. The computer then calculates the equivalent mass that the particle must have had. But out of the billions of photons, how do you know they actually came from a Higgs boson, and not from some other source? Well, imagine that you roll the dice 60 times. Normally, there's an equal chance of each outcome, so you'd expect about 10 of each number. But imagine that you roll the dice 60 times and you actually got more of a certain number. Let's say you got about 20 threes. You'd rightly suspect something was causing this. Well, scientists took 100,000 collisions and measured the energy of the gamma photons produced. They plotted the number of photons, or events, with certain energies. Now, with no Higgs boson, you'd expect the smooth blue line with more low energy photons and less high energy photons. But as they collected more and more data, they noticed slightly more gamma photons with an energy of 125 gigaelectron volts. This suggested that there was a new particle that had been found with that exact mass. Both the CMS and ATLAS detectors independently confirmed the finding to 5 sigma certainty. And in 2012, the announcement was made that the Higgs boson had been discovered. And the following year, Peter Higgs and his colleague Francois Elgert were given the Nobel Prize. If you like this video, please like and subscribe, and don't forget to watch my other videos as well.